You are sitting in a climate-controlled room right now. The temperature is regulated to within 2 degrees of your personal comfort threshold. You did not build the system maintaining that temperature. You did not design the insulation in your walls, calculate the thermal resistance of your windows, or engineer the convective airflow cycling through your vents. You simply exist inside infrastructure that someone else solved for you, and you have never once needed to think about the physics of staying alive in the cold. Now strip all of that away. Remove the grid, the gas line, the synthetic insulation, the double-paned glass. Drop the ambient temperature to -38 degrees Celsius. Add wind. Add darkness for 6 months of the year. Add the complete and total absence of any institutional knowledge, any written record, any inherited blueprint. That is the engineering problem that Homo sapiens faced approximately 20,000 years ago during the last glacial maximum, and they did not die. They did not retreat. They engineered their way through it with a sophistication that modern material scientists are only now beginning to formally recognize and document. What happened during the last glacial maximum was not a survival story in the romantic, cinematic sense that popular culture has conditioned you to imagine. It was not a tale of desperate, fur-draped figures huddled around accidental fires, waiting passively for the ice to recede. The archaeological and paleoanthropological record, when examined without the cognitive bias of civilizational superiority, reveals something categorically different. It reveals a species engaged in systematic, iterative, multi-generational engineering problem-solving at a scale and complexity that challenges every assumption embedded in the word primitive. The humans who lived through the last glacial maximum were not proto-civilized. They were fully cognitively modern. Their neurological baseline was identical to yours. The only variable that differed was the technological vocabulary they had inherited, and what they built from that vocabulary, under conditions of extreme thermodynamic stress, constitutes one of the most impressive engineering achievements in the entire span of human prehistory. The last glacial maximum, which reached its thermal nadir approximately 21,000 years before the present, was not a uniform environmental event. It was a cascading, continent-scale restructuring of atmospheric, hydrological, and geological systems. Ice sheets 2 to 3 kilometers thick covered what is now Canada, Scandinavia, and large portions of northern Eurasia. Sea levels were lower by approximately 120 meters. The permafrost boundary extended deep into what is now temperate Europe. The atmospheric concentration of carbon dioxide had fallen to approximately 180 parts per million, producing a global mean temperature reduction of roughly 5 to 7 degrees Celsius relative to the pre-industrial baseline. But the critical variable, the variable that drove the engineering imperative, was not the average temperature. It was the thermal volatility at the habitat boundary. The periglacial zones, those marginal territories just beyond the ice sheet margin, where Pleistocene human populations were concentrated, experienced temperature oscillations of extraordinary amplitude. A single diurnal cycle could swing 30 degrees. A seasonal cycle could swing 60. Survival in those conditions was not a matter of endurance. It was a matter of applied thermodynamics. The first engineering solution that the archaeological record documents with overwhelming consistency is what researchers now classify as composite structural architecture. The deliberate, calculated assembly of multi-material shelters using a framework logic that anticipates, in its fundamental geometry, the structural engineering principles that would not be formally articulated for another 15,000 years. The mammoth bone structures of the Eastern European plain, excavated at sites including Mezhyrich in modern Ukraine and Kashynki on the Don River, represent the most extensively documented expression of this engineering tradition. These were not simple windbreaks. They were not opportunistic assemblages of scavenged material. The Mezhyrich structure, which dates to approximately 15,000 years before the present, incorporated over 150 individual mammoth bones, many of which were interlocked using a mortise-and-tenon logic, a load distribution strategy that requires an a priori understanding of compressive and tensile force vectors. The base ring of the structure used mandibles arranged in a stacked, alternating pattern that modern structural engineers have identified as functionally equivalent to a corbelled foundation. The vertical elements used long bones oriented along their axis of maximum compressive strength. This was not accident. This was not intuition in any mystical sense of the word. This was empirically derived, generationally refined, materially specific structural engineering. But the structural achievement is only the outermost layer of what these builders accomplished. The thermal engineering embedded within these composite structures represents a separate and equally sophisticated domain of applied knowledge. The critical challenge in a paraglacial environment is not simply excluding wind. Wind exclusion is a first-order problem, and the mammoth bone framework, covered with layered hides using overlapping panel geometries that create pressure-equalizing airlocks at the entry threshold, solved it effectively. The second-order problem is radiant heat management. In an enclosed space heated by open combustion in a pre-industrial context, the primary mechanism of heat loss is radiative transfer through the structural envelope. The Pleistocene engineers addressed this through a layered insulation strategy that modern building physics would classify as a multi-resistance thermal assembly. Archaeological evidence from multiple Eastern European sites indicates the use of packed plant material, primarily compressed grass and sedge, as an interstitial insulating medium between the hide panels. The thermal resistance value of compressed dry grass is approximately equivalent to modern fiberglass batt insulation of comparable thickness. These populations had, through systematic empirical observation across generations, arrived at the optimal insulating medium available in their material environment and deployed it in a configuration that maximized its resistance coefficient. The third-order thermal problem, and this is where the engineering sophistication becomes genuinely remarkable, is internal atmospheric management. A sealed insulated enclosure heated by open combustion in a pre-industrial context faces an acute carbon monoxide and carbon dioxide accumulation problem. The combustion products of a wood or bone fat fire in an enclosed space of approximately 20 to 30 cubic meters will reach lethality within hours if the ventilation architecture is not deliberately engineered. The resolution of this problem requires understanding, at some functional level, the relationship between combustion chemistry, atmospheric circulation, and structural aperture geometry. The archaeological evidence suggests that these structures incorporated controlled ventilation apertures at the apex of the dome, positioned to exploit the thermodynamic principle of convective stack effect, the natural tendency of heated air to rise and exit through a high aperture while drawing fresh air through a lower intake. This is the same physical principle that governs the ventilation architecture of Gothic cathedrals, Victorian industrial buildings, and modern passive house design. The Pleistocene engineers arrived at it not through formal fluid dynamics but through the most rigorous laboratory available, the recursive, generational process of building structures, living in them, observing the outcomes, and refining the design. The engineering vocabulary of the last glacial maximum extended far beyond permanent or semi-permanent structures. The mobile populations of the northern paraglacial steppe, the groups following mammoth, reindeer, and horse migrations across seasonal ranges of hundreds of kilometers, faced a distinct and in many ways more demanding engineering challenge: the design of portable thermal enclosures that could be assembled and disassembled rapidly, transported across variable terrain, and reconfigured to respond to changing environmental conditions. The archaeological and ethnoarchaeological record, supplemented by analysis of surviving cold-adapted populations in Siberia and the Canadian Arctic, whose material culture preserves deep continuities with Pleistocene practice, points to a portable shelter technology of extraordinary refinement. The fundamental design parameter was the optimization of the surface area-to-volume ratio of the enclosed space. A hemispherical enclosure, for a given volume of heated air, presents the minimum possible external surface area through which heat can be lost. This geometric insight, which is a direct consequence of the isoprometric principle of mathematics, is encoded into the design of every traditional Arctic dome shelter. These populations had solved an optimization problem that would not receive formal mathematical treatment until the 19th century. The thermal management systems of the last glacial maximum were not confined to architecture. The most intimate and perhaps most technically sophisticated thermal engineering of the period occurred at the level of the human body itself, in the design and construction of composite clothing systems. The evidence for tailored, fitted garments during the Upper Paleolithic is now extensive. Eyed bone needles, recovered from sites across Eurasia dating to 30,000 years before the present, indicate the capacity to produce sewn, fitted garments with precision tolerances measured in millimeters. The distinction between a draped hide and a tailored, fitted garment is not aesthetic. It is thermodynamic. A draped hide creates irregular air gaps at the body's surface that function as convective channels, allowing heated air to escape continuously. A fitted, layered garment system, particularly one that incorporates a wicking inner layer, an insulating intermediate layer, and a wind-resistant outer layer, creates a controlled microclimate at the skin surface that dramatically reduces convective and evaporative heat loss. This is the fundamental architecture of modern technical cold-weather clothing. Every Gore-Tex cell, every down-filled mid-layer, every moisture-wicking base layer manufactured by contemporary outdoor equipment companies is a direct functional descendant of the composite garment systems engineered by Upper Paleolithic tailors working with bone needles and sinew thread in the workshops of glacial Eurasia. The energy systems that powered the domestic infrastructure of the last glacial maximum represent another domain of engineering achievement that has been systematically undervalued. The primary combustion fuel of the Eastern European paraglacial steppe, in many regions almost entirely devoid of arboreal vegetation, was not wood. It was bone fat, the rendered lipid content of the large skeletal elements of megafaunal prey species, primarily mammoth. Bone fat combustion requires a delivery mechanism, a wick or reservoir system that maintains a controlled fuel-to-oxygen ratio at the combustion interface. The stone lamps recovered from Upper Paleolithic sites across Europe and Siberia represent precisely this technology. These were not primitive equivalents of the campfire. They were precision combustion devices, engineered to deliver a controlled luminous and thermal output from a low-volatility lipid fuel. The geometry of the lamp bowl, its depth, its aperture angle, its surface texture, directly affects the capillary dynamics of fuel delivery to the wick. The variation in lamp morphology across geographic regions and temporal periods reflects a process of iterative design refinement, empirical engineering operating across generational timescales. What makes the engineering legacy of the last glacial maximum so cognitively disorienting for a modern audience is not any single technical achievement, but the systems-level integration of those achievements. These populations were not solving isolated problems. They were managing an integrated technological ecosystem in which structural engineering, thermal management, materials science, combustion chemistry, and garment design were all simultaneously optimized and mutually dependent. The failure of any single subsystem, a structural joint that could not bear the compressive load of accumulated snow, a garment layer that could not manage moisture vapor transmission, a ventilation aperture that could not maintain combustion byproduct concentrations below toxic thresholds, had immediate, potentially fatal consequences. The selection pressure for engineering competence during the last glacial maximum was absolute. There was no margin for design failure. And the populations that survived, the populations whose genetic and cultural heritage flows directly into every modern human alive today, survived because they engineered solutions that worked, generation after generation, across 20,000 years of one of the most thermodynamically hostile environments in the history of the species. The technology they developed did not disappear when the ice retreated. It was not rendered obsolete by the Neolithic transition. It was abandoned gradually, selectively, and in many cases prematurely, as populations migrated into warmer latitudinal zones where the full thermal management repertoire of the glacial engineering tradition was no longer immediately necessary for survival. The knowledge was not written down because writing had not been invented. It was encoded in practice, in the embodied knowledge of skilled craftspeople, in the oral traditions of communities whose survival depended on the accurate transmission of technical information across generations. When the communities dispersed, when the ecological context that had made the knowledge critical shifted, the transmission chains broke. The engineering solutions of the last glacial maximum did not fail. The civilization that carried them simply moved somewhere warmer and forgot to bring everything it knew. We are now, in the early decades of the 21st century, in the process of rediscovering what was forgotten. Materials scientists at institutions across Europe and North America are formally studying the thermal resistance properties of Pleistocene-era composite high-end fiber assemblies. Structural engineers are analyzing the load distribution geometry of mammoth bone frameworks using finite element modeling software. Cognitive scientists studying the neurological correlates of technical skill acquisition are beginning to map the specific domains of expertise that must have been present in Upper Paleolithic populations to produce the material record that archaeologists are recovering. What they are finding, consistently and across disciplines, is that the distance between the glacial engineer and the modern one is not a distance of cognitive capacity, or of fundamental intelligence, or of the basic human drive to observe a problem and build a solution. The distance is almost entirely a matter of vocabulary, of the specific technical language, the specific material palette, the specific institutional framework within which the engineering intelligence of Homo sapiens has been deployed in different eras. Strip away the vocabulary, and what remains is the same mind, the same capacity for systematic observation, the same iterative refinement, the same willingness to stake survival on a design decision made in the cold and the dark, with nothing but accumulated empirical knowledge and the engineering instinct of a fully modern human brain. The Ice Age was not a pause in human history. It was not a waiting room where a cognitively limited ancestral population endured until the climate became hospitable enough for civilization to begin. It was an engineering examination of the most severe and unforgiving kind, administered by a planetary climate system with no tolerance for failure and no partial credit. The humans who sat that examination did not merely pass. They produced a body of applied technical knowledge in structural mechanics, thermodynamics, combustion engineering, materials science, and wearable technology that represented the state of the art for their material context, and that in several domains has not been meaningfully surpassed by their descendants. We inherited their biology. We inherited their cognitive architecture. We inherited, in attenuated and often unrecognized form, fragments of their technical tradition. What we abandoned, along with the cold, was the understanding of just how sophisticated those who came before us truly were.